cat corresponds to 12, dog corresponds to 7, and fox corresponds to 12, whatever that may be. But this represents a correspondence between two sets, and that's what we mean by when we say a relation. So again, relation, correspondence between two sets. And most of the sets that we're going to encounter will have some numerical elements in them. And if we do this, and I say here we have -1, 0, and 1, then here we have values 1, 2, 3. And let's say 1 goes to 2, 0 goes to 1, 1 goes to 3, or something like that. Then this would also be a relation. And any relation, we can write it as a set of ordered pairs, because an ordered pair connects two values, one from the first set, and the second one is going to be from the other set, from the second set. So if we use a set of ordered pairs, we can also write down this relation using a different format, basically. So if this is my domain and this is my range, and I have the following correspondence between my elements, then -1 corresponds to 2. So that's one ordered pair. I can have 0 corresponds to 1. So that's my other ordered pair. And here I have 1 corresponds to 3. So this would be equivalent, and that would give us the same exact relation. And if I gave you the set of ordered pairs, I can say, well, what is the domain? And you can generate the domain just by listing the set of all the first elements, right? The domain is the set of all the first elements of these ordered pairs, so all the x's essentially. So the domain here would be -1, 0, and 1. In no particular order. There is not necessarily an order that needs to be present here. And the range would be 2, 1, and 3, or the set of all the second components of these ordered pairs. Now, because we have ordered pairs and we know that we can graph ordered pairs, we can plot them, that gives us a rise to yet another representation of relations, which is their graphs. If we plot these points on XY coordinate plane, then that will also give me a different representation for the same exact relation. So let's do that as well. So I have -1, 2. That can be represented with an ordered pair. I have 0, 1. That can be represented as an ordered pair. And I have 1, 3. That is also an ordered pair. So all three of these are representing the same relation in different ways. There is also going to be another representation, but we can't really use it here because our domain and range are finite. There's only 3 elements in each one. But if we have infinitely many elements, then oftentimes we will use equations, or not just plotted points, but actual graphs, smooth curves, to represent these relations. So again, relation is just a correspondence between two sets, and those two sets, they have a name. The first is the domain, and the second set is the range, and also refer to them sometimes as input and output. Now let's move that a step forward and say, well, what makes a relation into a function? So a function is still a relation, right? So it still is going to be a correspondence between two sets, but it's a more strict correspondence. We have another clause basically that has to be satisfied. So we're going to define what it means to be a function. we will start by saying that the two sets, x and y, are non-empty. So x and y are non-empty sets. Then a function from x to y, so again, x is the input, y is the output set, so a function goes from the input to the output. So a function from x to y is a relation with one more condition. So it's a relation that maps, well, let's not use that word actually. So let's say it in the following way. It's a relation where each element in X, which is again the domain, corresponds to exactly 1. And that's the key word here. That's that requirement that tells apart a function from a simple relation. So each element in X corresponds to exactly 1 element in Y, the range. So that's how we would define a function. So it is still a correspondence between two elements, but it's a correspondence such that all the elements in the domain, any one of them you pick, only goes to one element in the range. So to make it into a little bit of a more clear example, let's consider these two cases. Let's say I have my domain and my range, and here I have A, B, C, and here I have 1, and A corresponds to 1, B corresponds to 1, and C corresponds to 1. Let's make it 10 for unknown reasons. So is number 1, what class, let's see, what classifies it as non-empty? So non-empty means that there are elements in there. We cannot talk about a function if one of the sets is empty. It's got to contain stuff. It's got to contain elements in it. So if I put nothing here and I put 5 here, it doesn't make sense to talk about any sort of correspondence between this empty set and some other set. So that's all that we mean by non-empty. So for number 1, the question for both of these is, are these relations representing functions? So is number 1 a function?
Yes.
No.
So let's think about that. Look back at the definition.
No, it's not.
So each element in X, or each element in a domain, let's call it the domain at this point, corresponds to exactly 1 element in Y. So let's start. Yes. Yeah, the answer would be yes. Let's start with the first element in a domain, A. How many elements does it correspond to?
1.
1 element.
1.
Element B in a domain, how many elements does it correspond to?
1.
1. Element C in a domain also corresponds to 1 element. So each element of my domain corresponds to exactly 1 element of my range. It happens to be that the element they correspond to is the same element, but that is not part of this definition. Later on, we will have even a more strict definition for a function. It will be called a one-to-one function. And that will basically say that not only do they have to correspond to 1 element, but they have to correspond to different elements. So it'll work both ways. But that's not part of this definition. So this would satisfy a function definition. This is a function. So yes, this is a function. For number 2, I guess I should phrase a question here. So I'm asking, is this a function? And same thing here, I'm asking, is this a function? For number 2, let's say we have 1, 2, 3, and we will have A, B. And then 1 goes to A, 2 goes to A, 3 goes to B. Would this be a function?
Yes.
No.
So again, look at only at your domain. Your domain is what determines whether you've satisfied your definition.
Oh, really?
Because from your domain, if every element has exactly one correspondence, then you have a function. 1 corresponds to a single element, 2 corresponds to a single element, 3 corresponds to a single element. This is still a function. Again, it happens that 1 and 2, they correspond to the same element A, but that does not break the definition of a function. So this would be a function. Again, domain is what you're concentrating on to figure out if you have a function or not. Let's do another one. Let's say we have -1, 1, 2, and let's say we have 1, 2, 3, 4. So let's say -1 goes to 1, 1 goes to 2, 2 goes to 3, 2 goes to 4. Would this be a function?
No.
No.
So this one is not a function. This one would be a no. And again, you would check your domain elements. This guy is okay, right? Goes to one element. This guy is okay, goes to one element. But as soon as there is one, even one, it could be multiple, but as soon as there is at least one element in the domain that has 2 correspondences, that goes to 2 elements in the range, that breaks our definition. So that would not be a function because the element 2 corresponds to element 3 and element 4. So this is not a function. Are we okay now on this definition here of a function?
Yes.
A little better.
I have a question.
Yeah, go ahead.
If we leave, like, we have -1 for 1, 1 for 2, and we leave 2 just free and don't do anything for 4, just leave it as it is it possible or it can't exist?
So we for now, let me think how to actually properly respond to that. So for now, no. So you're not going to deal with any sets where an element has no correspondence to it. So for now, you're not going to see any of the examples like that. So every element in a set has to have some correspondence for our discrete sets. So we have to be able to, so so you're saying basically this, if we have elements here like 1, 2, 3, and then we have elements here like, let's say -1, -2, -3, and 4, then the correspondence is this goes here, this goes here, this goes here, and the 4 is just kind of hanging around, right?
Yes.
Yes, so we're not going to consider such examples because we need to have correspondence. We need to have correspondence to 4 from somewhere. So it has to come from somewhere. This output has to have some input. So those cases are not going to be considered as relations or functions because you have like a free floating member that doesn't come from anywhere. So it wouldn't be part of our discussion.
Okay, thank you.
So we will have, for every output, there will be some sort of an input where it comes from. And if there is a single input for multiple outputs, then we say it's not a function. But yeah, no free floating no input without an output, or vice versa, because then you don't have a correspondence. You don't have the ordered pair correspondence. All right, so now that we kind of understand this concept of a relation and a function a little better, let's also talk about equations representation. So these were all discrete examples where our domain, our range, were just a few numbers or a few things, like a cat and a dog and a fox and one of them, right? But we can talk about equations also representing functions. So if I gave you something like this, y equals, let's pick something simple, 3x plus 1. So this is an equation, and it has it has x and it has y. Now, if I don't say any restriction on x, then I'm free to choose any x value that I want, any real number for x. Now the question is, this definitely gives us a relation, because if I pick x to equal to anything, if I pick x equals 2, for example, then there will be a corresponding y. So for any x I choose, there's going to be a corresponding y value. So if x is 2, then y is going to be 7 in this case, right? So I can put 2, 7 as an ordered pair, and I can generate infinitely many ordered pairs. If x is equal to -1, for example, -1, I plug that in for x. 3 times -1 is -3, plus 1 is -2, so I get another ordered pair, and I can keep doing that forever, right? So there's infinitely many ordered pairs, but it's not just integers, right? We can also plug in rational numbers, irrational numbers. So we can basically plug in any real number for x and get a corresponding value for y. So we can generate many of these x comma y ordered pairs, infinitely many. But how do we actually determine if this equation represents a function? So the question is still the same. Does this represent a function? And the answer will come by remembering our algebra. So if I plug in a unique x into this equation, is there any way that I'm getting two different y values? Is there any way to plug in some x so that I get a different y and another different y for that x? Well, there's no way of doing that, right? There's only one y for whatever x I plug in, because of the algebra that we're doing. We're taking, right, again, remember, think of this as this machine that takes in an input and produces an output. And if for every input there is a unique output, then it's a function. And here, if I put in some value, some number, then this function tells me do what with that input. Multiply it by 3, whatever is that input, whatever is that x that goes in there, and then add 1. So for every unique value that I put in as an input, there's going to be a unique output. I cannot get two different outputs from this, from this machine, the way that it's set up, from this 3x plus 1. So this equation represents a function. And when you're given an equation, in order to check if it represents a function, the easiest way is to solve for y, or, and that's going to be more so for the next lecture, or graph. For now, we will concentrate on this part, on solving for y, because once we've solved for y, we can much easier see if we can get multiple outputs from a single input, just by remembering our algebra and how to solve things for y. In this case, it was already solved for y. It didn't really have to do anything. But in some cases, you can have an equation, something like, hopefully you guys did your circles. if I gave you x squared plus y squared equals 9, right? This is an equation. As a matter of fact, and we'll consider both options here. We will consider a graph of this. Do you guys recognize it as a circle? If you watch the video on 1-4, what would be the center of this circle?
0, 0.
The center,
0, 0.
yeah, the center would be 0, 0. And what would be the radius of this
Right.
circle?
3.
Right.
Yeah, this radius, square root of 9 would be 3. So if I graph this circle, then we will kind of already know the answer, whether it's a function or not. As a matter of fact, it's true for, it's hard to do circles. Good enough. So any circle, is that a function or no?
No.
So the answer would be no. And one easy way we can see that it's not a function is if I pick basically any x which is part of the domain. Again, we will discuss the domains for circles a little closer later on, but let's say I pick x is equal to 1. So let's say I pick x is equal to 1. Well, when x is 1, I have a y value here. Let's call it y sub 1. That corresponds to this x, but I also have some other y value. Let's call it y sub 2 down there. So this is saying that for one input, I have two different outputs. One of them is y sub 1 and the other is y sub 2. I mean, we can plug it in and we can find out the exact value. It's not that difficult. But here I'm just saying in general, there are infinitely many x values that I can pick that will be in the domain of this graph that will generate two values, two outputs, two different outputs, making it not a function. So from the graph, it's fairly easy to see that. And as a matter of fact, we will define this as a vertical line test in the next lesson. So there's a vertical line that crosses the graph at 2 points, making it not a function. But from the algebra perspective, looking at this equation, we can also show that. And what we're going to do is we're going to solve for y. So if I take this equation and I solve it for y, I would have to move x squared to the other side. Now, how do we undo the square? How do we go from y squared to just y?
Square root.
We have the square root property. But if you guys remember the square root property correctly, what should we put in front of the square root?
Plus minus
Yeah.
arrow.
We have to put in the plus minus. Whenever we square root both sides, whenever we use the square root property, we have to put plus minus. So now we've solved for y, but what is this really? Plus minus means I have two equations. One of them is the positive square root of 9 minus x squared, and the other is the negative square root of 9 minus x squared. So here we can see that basically for almost any value I choose for my x, there's always going to be two corresponding y values for almost any value that I choose, right? Except unless I choose 3 or negative 3, those are the only two values that only have one correspondence. But remember, as soon as you find even one, based on this example, even one element in a domain that corresponds to more than one element, to two elements in this case, but more than one element, that breaks the function definition. And here I have infinitely many. If I choose, we already saw, if I chose x equals 1, I'm going to have two different y values, right? One of them is going to be positive square root of 8. If I plug in 1, here I'm going to have positive square root of 8. And here I'm going to have negative square root of 8. So I have two different outputs. And I can pick, I can pick 0. If I plug in 0, I'm going to have, so if x is 0, then I have y equals square root of 9, which is 3. And I have y equals negative square root of 9, which is negative 3. So again, I have one input corresponding to two outputs. So here from the equation, because of that plus minus, we can see that it is not a function. Without graphing it, we should also be able to detect that. So if you encounter square root, where you have to square root both sides to isolate your y, or also maybe it's worth mentioning absolute value. If I gave you something like this, if I gave you, let's say, absolute value of y plus 3 equals x minus 7. And I would ask you, let's solve for y. Let's solve this for y. Do you guys remember how to solve absolute value type equations? How can I solve this for y? What should I do here?
You can just take all the absolute signs and solve as it is.
No. We can't just ignore the absolute values. So if you guys
Just
think,
write y plus 3 more than 0, more or equal to 0.
well, but what if it's not? So we can't impose our own requirement. So there was a property in algebra that you guys might have hopefully seen, which says if you have absolute value of something and it's equal to some value, then what you're supposed to do is you're supposed to consider two equations. One of them is the positive version and the other is the negative version. All right, so does that ring a bell? You guys remember seeing that, solving absolute value equations, where you split it up into two?
Yes.
So that's what should come in here. If we try to isolate y, we first have to take care of the absolute value, but to do that, we would have to consider the positive. So if y plus 3 is positive, then we would have this equation. Or if y plus 3 is negative, then we would consider this equation. So there's two equations, and the result, if we solve for y, on one of them is y equals x minus 10, and on the other one, we would have to distribute that negative sign, move the 3 over. The result is, again, two different equations. So what that means is if I plug in an x, any x really, so let's say I choose x to equal to, I don't know, 5 or something like that, then I get two corresponding y values for any x that I choose. So if I plug in 5, I'm getting x minus 10, so that's 5 minus 10 for the first value, and I'm getting y equals, so negative 5 plus 4, negative 1. So in this case, we can also show that if I solve for y, because I get two different equations, then basically for any x input, I'm getting different y outputs, two different y outputs, so this would not be a function.
Professor?
Yes.
I'm still not I can't understand why you created the negative x minus 7 with the absolute value.
So that goes back to algebra definition discussed here. In algebra classes, you guys were solving equations that contain absolute values. So maybe let's do a quick recall. If I ask you to solve x plus 5 equals 3, right, then you were introduced to this concept of absolute value equations, and later on absolute value inequalities, which says that to solve it, you need to consider x plus 5 equals 3 or x plus 5 equals negative 3. You need to solve both of these equations, right? Because from here you would get x equals negative 2 from this equation, you would get x equals -8. So if I plug in -2 into the original, then what would happen? Absolute value of -2 plus 5 equals absolute value of 3, which equals to 3. So that's a true statement. If I plug in -8 into the original, I get absolute value of -3, which is still 3. So that is a true statement, right? So most absolute value equations have two solutions. And that was a property that we used here to find both of the solutions. Here, we weren't necessarily looking for numerical solutions. We were solving for y, but it's the same property that we have to use. We have to consider the positive and the negative.
Got it. Thank you, Professor.
Now, to go into a deeper explanation, how come we have two equations, that'll actually come in a little later in this class when we define piecewise functions, because actually absolute value is a piecewise function. It acts in one way on a certain portion, and then it acts in a different way on a different portion, on a different piece. So in algebra, you were just given this definition, but later on we will see why such definition exists. So for some of your homework questions, you guys will be given these, these equations, and you'll be asked, is this a function? Is this a function of x? And basically, if you need to solve for y, that will help you figure that out. All right, next we want to introduce function notation. We want to say, well, if we know that we have a function, so if we know that our equation is actually a function, what would be an easier way of working with that function? Instead of making little tables or saying if x is so, what is y? So that's where the function notation comes in. Function notation. Let's say we have the following equation: y equals -2x squared plus 5x minus 10, or something like that. So there's an equation. It is already solved for y. Now, by looking at this, do we all agree that this is a function? That this is indeed a, let me choose a different color. That this is a function because any x that I pick, there's only going to be one y that results from any given x. It's already solved for y, so all I can see, I can see that whatever x I plug in, I'm just doing some operations to it, and I can't do an operation like a square or a multiply or an add or subtract that gives me two different results, right? It doesn't work like that. If I square a number, I'm getting a unique value. If I multiply a number by -2, I'm getting a unique value. I cannot get two different values if I multiply something by -2, or if I add 10 or subtract 10. So this is a function. Now, what we introduce here is what's called a function notation. So we're going to name this function. Let's call it f for function. That's probably the most common name, but you could also have g or h, or really anything but f, g, and h are probably the more commonly used names for functions. So then we can rewrite this guy using function notation. We can say that this is a function where the input is x, and it is defined in the way of -2x squared plus 5x minus 10. So this is pronounced f of x, f of x, and f tells us the name of the function, and x tells us that that's the input. And then after the equal sign, we have basically the stuff that tells us what to do with the input. So in this case, we are going to square the input. We're going to multiply the result by -2. Then we're going to add 5 times the input, and we're going to subtract 10 from the result, right? That's what this function does. So again, it's a machine that takes in inputs, produces outputs, and in this particular case, this machine is called f, this function is called f, and what it does to the input is it does all these things to it, right? Like that. So if my input happens to be 3, then using this function notation, I would just say f of 3. My input is 3. And f of 3, the result, the output, is going to be whatever f of 3 is equal to. Whatever f of 3 is equal to, and we would have to plug in 3 instead of my input and simplify it to see what that output will be. So 3 here is my input. Let me color code it. And we're plugging it in instead of x, whatever we saw this x in my function. Apply your order of operations, -2 times 9 plus 15 minus 10. That's -18 plus 15 minus 10. That's -3 minus 10. That's -13. Yes, so -13 is right. So f of 3 is equal to -13. That's using function notation. But we can, so let's put that here as well. The output here is -13. But remember, when we were talking about functions earlier, somewhere over here, right, input output, we were saying that if x is the input, then y is the output, and we had ordered pairs for that. So we were representing those things with ordered pairs, as we were doing here as well. So function notation and ordered pairs are again just different representations of the same thing. I can use ordered pair notation to write this as well. What is my x value for that function notation?
3.
Yeah, 3. And what is my corresponding y value?
-13.
13.
-13, yeah. And we know that if we want, we can plot ordered pairs. So there is a very tight relationship between graphs, ordered pairs, and function notation. They all kind of represent the same thing in different ways. And that'll be a very important point for us to explore when we talk about graphing, that again, these are all related. They're all sort of saying the same thing using different notation. So now we have function notation and we have ordered pairs, but we know that ordered pairs are just points on the graph. So that will all come in very handy. Now let's do another example just to solidify our function notation understanding. Let's say I have a function, let's call it g of x, capital G, so lowercase or uppercase, those are just names of functions, so it really is not too important. There's nothing that says you cannot use a different letter of the alphabet. You can call it k of x or a of z, it's just names. Now let's define it as 2. We'll still stick to squares, -7x plus 5, and I will ask you to find g of, we'll do this 2 parts. Part A, we'll do g of a squared. So our input here is an expression, not a numerical, but an expression, but that's perfectly fine. We should be able to do that. And here we're going to do g of a plus b to remember a few things. So I'll give you guys about 5 minutes where I'll go on mute and let you work on it. And in about 5 minutes, we're gonna go over it and see what you got. Alrighty, so I see some of you are writing some answers, and yeah, like you can see that, you know, typing math isn't always easy, but you can always, if you have a question, you can always write something out on paper, snap a picture and email it to, or, you know, Canvas message it to me, and I'll reply in kind of a similar way. Or if you have some sort of a iPad or Surface, Microsoft Surface or whatever, you know, tablet, you can write things down and send them like that. That's also pretty convenient. But let's see what we got. So you'll remember some algebra properties here, which is a good thing, I think. We have 2 input squared minus 7 times the input plus 5. And for part A, our input is this guy, a squared, this expression, a squared. So then, probably should have made it a cubed to make it a little more interesting, but regardless, properties of exponents, right? So one of the properties that we're trying to remember here, so we'll call it like recall. Property of exponents, if you have a to the n raised to the power of m, what should that equal to?
We just multiply them, a and multiply them.
Yeah, so we would multiply the exponents, n times m is correct. So here we would do 2 times 2, which would give us 4. Here we would just have minus 7a squared plus 5, no like terms. That's as far as we go. Right, so that would be our final answer. 2a to the 4th minus 7a squared plus 5 is good. For part B, similar, right? We still have our 2 times the input squared minus 7 times the input plus 5. So it's the same function, but our input here is a binomial, 2 terms, right? Binomial, a plus b. So here we have another property we want to remember, which is called binomial squared, a plus b squared. What does that give us if we square
A
something like
squared
that?
plus 2ab plus b squared.
That's good. So a squared plus 2ab plus b squared.
I forgot.
You guys forgot? Oh, that's okay. That's okay. I hear some sides, you know, but mainly if you square a binomial, make sure you guys do not simply distribute the exponents. So if I have a times b, for example, squared, then that's just a squared times b squared. That's the easier one. But as soon as we put in addition or subtraction, as soon as we have multiple terms in there, then you got to be careful not to make the same mistake and say something like this, right? That is not a true statement. So that middle term has to be in there when you square binomials. So then when we keep simplifying it, we're going to see the following: 2 times, and then we got a squared plus 2ab plus b squared. We can distribute this negative 7. That's not a problem. So it's minus 7a minus 7b plus 5. Then we would still need to distribute this 2 because we have 3 terms in there. So it's a 2a squared plus a 4ab plus a 2b squared minus 7a minus 7b plus 5. So all of that would have to be our final answer. So yeah, if you guys forgot, for either the property or to distribute, again, there's quite a few steps in there, but it's not overly complex, I would say. But this was a good reminder for our next example. So our next example is we're introducing something that is called a difference quotient. It will not really be used until probably the beginning of your calculus class. If we have time, not always, but if you have time, we might talk about it later in this class. But the difference quotient is something that you use to introduce a very important concept in calculus: derivatives. And the difference quotient is defined in the following way. So if you have a function f, so f again is the name of the function, that's all it is here. F is our function, then the difference quotient for this function is defined as the following quotient. F of x plus h minus f of x over h, where h is not equal to 0. Where h is not equal to 0. So again, this is just a specific, specific quotient, specific expression that for now might seem like, well, why do we need to do that? But later on, it will be pretty important in the definition of an integral part of calculus, important part of calculus, I should say, because one of them is called integrals, the other is called derivatives. So this will be used to define derivatives. But for now, we're sort of just after the algebraic part of it, how to actually, how to apply a difference quotient to a function and how to simplify it. But that's what we define the difference quotient to be. So you see that it has 3 parts, right? It's got 3 parts to it. In the numerator, you have one part minus another part, and then you divide all that by the third part, which is h. So the first part is the function evaluated at this binomial x plus h. The second part is simply the function itself and then divided by h. So that's how we're going to attack this problem. We're going to first find what is f of x plus h and then plug everything in and simplify. So let's see how that looks. We'll pick one example to do here. And I'll pick sort of medium difficulty and not too difficult, not too easy. I think 88 will be okay. Directions is find the difference quotient, and the function given to us is a quadratic. F of x equals 3x squared minus 2x plus 6. So again, as we mentioned, the difference quotient is defined to be f of x plus h minus f of x over h. But we'll do this with a little bit of scratch work, and I hope I can have enough space to fit it all. So the first part is I'm just going to find what is f of x plus h. So all I have is my function f, and I want to evaluate it at this input, which is very similar to what we just did in the previous example. So my input here is this x plus h, again, x plus h. And we just did a input of, where was it here, a plus b. So we were already introduced to squaring something like a plus b and remembering the formula, distributing. So we're going to do a very similar process here. We're going to square x plus h using the same formula. That'll give us 3 terms, right? X squared, 2xh, and h squared, similar. We're going to distribute the negative 2, add the 6, and then we also want to distribute the 3 here to each of these terms inside the trinomial. So it's a 3x squared, 6xh plus 3h squared, bring down the rest of the terms. So this part here is simply the first term of my quotient, of my difference quotient. f of x, I already know that, so I'm still going to write it out here. F of x is 3x squared minus 2x plus 6. That was already given to me. And then, of course, h is just h. H is a single variable, so that shouldn't be too bad. So this is my scratch work over here. Now for my neat work, I'm going to say that this equals the following. So f of x plus h, I'm going to write it in green here. I have 3x squared. I'm still going to put it in parentheses just to kind of, for visual reference, plus 6xh plus 3h squared minus 2x minus 2h plus 6. Then I have a minus sign. And then I have my f of x minus f of x, which is 3x squared minus 2x plus 6. And all that is divided by h. So that's what my difference quotient looks like. Are we still okay? Are we still okay as to where those expressions came from?
Yes.
If you guys have questions, feel free to ask. And if the explanation doesn't take too long, I'll be happily explain it. But if it's something that goes back to some algebra property and it would take me a while, then I might just kind of reference and say, all right, try to see polynomials or try to see properties of exponents or something like that. And then you can maybe look it up after the lesson. All right, so next we're going to say, let's stick to blue, I guess. We're going to say this minus sign plays a role. It needs to be distributed. So let's bring down 3x squared plus 6xh plus 3h squared minus 2x minus 2h plus 6. A lot of terms, but nothing overly complicated, just distributing some things here and there. When we distribute the minus sign, we get minus 3x squared plus 2x minus 6. All that divided by h. Now we will start combining like terms in the numerator. I see I have 3x squared and negative 3x squared. Those add up to a 0. I see I have a negative 2x and a positive 2x. Negative 2x plus 2x is 0. I see a positive 6, negative 6. Positive 6 minus 6 is 0. So all the terms that did not have an h, we were able to cancel them out, leaving me with 6xh plus 3h squared minus 2h over h. So I'm only left in the numerator with terms containing h. And before we can reduce something, we have to make sure it's factored. So now we have to remember a little bit of factoring. Numerator has a GCF of h. I can factor it out from each term, leaving me with 6x from the first term plus 3h from the second term minus 2 from the third term. So only now I can say h and h are common factors that I can reduce. And there is my final answer. 6x plus 3h minus 2 is my final answer. So there is a bit of steps here. And of course, it's easy to make mistake, lose a negative here or there, and it kind of messes up the whole process. But hopefully you guys are going to be careful and not make those mistakes. Then you would get your correct answers. But
Can I
some
ask
of
you
them,
something?
yeah, go ahead.
In the final result, can we just divide them separately, like 6xh divide 2h and 3h squared divided to h and minus 2h divided to h.
So the answer is yes, that would be absolutely correct algebraically, and it would give you the same answer in this case. The only issue, and it's not even an issue, it's sort of like to make sure that you did everything correctly, you want to make sure that every term left behind contains an h. Because if you made a mistake and some of the terms in the numerator do not have an h, and you just go on and divide things by h, then you'll still have an h in the denominator, and that tells you that you made a mistake. So for me, I just do the factorization to make sure that every term contained an h, and I'm able to reduce the h entirely out of the denominator. Now, the logic behind it is because when you get to calculus, you're going to say, let's look at this as h goes to 0. So if there's still an h in the denominator present, you get undefined expression because you have division by 0. But again, for now, since we don't have that, then that doesn't make too much sense why we're so worried about this h getting reduced in the denominator. But we want to make sure that h is completely gone from the denominator. So if you split it up among all the terms and divide each term by h, that's perfectly fine as long as it reduces in every term.
Okay.
All right, so that was our difference quotient. And some of the questions you might see in your homework will be even, more algebraically involved. So that could get pretty tricky, but give it a try. The next part of this lesson will deal with concept of domain, but domain of a function which is expressed using function notation, so using equations, not just some bubbles of domain and range where it's easy to just read off and say, oh, this bubble is the domain, or the first ordered pairs is the domain. So if you have an equation in function notation, then the definition for domain is a little more difficult. We cannot just say, oh, it's the first set. We have to be more specific. What can that first set be? So if we're talking about a domain, let me put in the name of the function. Let's say domain of a function f. Then we define it in a way that it's the largest set of real numbers. So we might need a bit of a refresher what it means to have real numbers, for which the value of f of x is also a real number. So when we say real numbers, not all numbers are real numbers. Most of the numbers that we dealt with in algebra, most of the numbers we're going to deal with in pre-calc and then later in calculus are going to be real numbers. But what is, if a number is not a real number, what else can it be? What are our options? What was the set that we introduced in algebra?
Rational and irrational numbers.
So that would be part of real numbers. So we have this set and all of these are real numbers. It's kind of split into two parts. One part is rational. The other part is irrational.
Imaginary numbers are unreal.
Yeah, so that's the bigger part of this. There's a bigger part here, which is called complex. Complex, and we define complex numbers through imaginary unit, right? So when we say imaginary, that's part of the complex number. But inside the complex numbers, we have the set of real numbers, and that's the one that we mostly work with, right? They're split into rational and irrational. Irrational is something like pi or square root of 2. Rational means you can express it as a fraction, so something like 1/2 or, 7/5, who knows. But inside the rational set, we have a smaller set in here. Those are the integers, right? So that's how things look. But we have these complex numbers that are of the form a plus bi. If you guys remember that from algebra, there is this complex form, which is introduced by defining I as square root of negative, right? Square root of -1 is how we define the imaginary unit. So again, this is covered in algebra. We're not going to go into too much detail on it now. We don't need it so much now. We will need it a little more later, so we'll spend some time on it later. But just to refresh your memory, real numbers means that they are defined. First of all, a number has to be defined in order to be real, and also it cannot contain square root of a negative in order to be a real number. So for now, for our domain, we only have really two things to watch out for in the beginning. We have to have the number defined. It has to be defined. And what do we know is not defined? What's undefined when we work with numbers? I is defined, but it's not real. I is defined as square root of -1. But what operation is undefined? When we do something to numbers, we say, oh, it's undefined. Division.
0?
Yeah, division. Division by 0 is undefined. Right, division by 0 is undefined, which means it's not a real number. So if you have some sort of division, we have to make sure that it's not division by 0. And the other red flag is even roots. Mostly it's going to be square roots, but to be more precise, we will say even roots of negative numbers. That is complex. So what we mean by undefined specifically not real, right? It's not defined, so it cannot be real. Complex also means it's not real, not a real number. And for our definition, we have to have a largest set which produces real numbers. So these are the two things we basically have to watch out for. We have to watch out for denominator having 0, and we have to watch out for square roots of negative numbers. And those parts will need to be excluded from our domain. And if nothing is included from our domain, then it's going to be the set of all real numbers. So anytime you have a function that is a polynomial. So again, we're going to review a lot of these concepts, but if you guys already remember some of these names, polynomials, for example, anytime you have a polynomial, so a linear function is a polynomial, a quadratic function is a polynomial. So something like we saw here in 88, 3x squared minus 2x plus 6, that's a polynomial. Those will always have a domain of all real numbers because there's no roots in there, there's no division in there, so the domain is all real numbers. I can plug in any number and the output is also a real number, so nothing breaks it. So if we see something like number, let's see where our domain questions. I guess something like 52 or something like number 51. I don't know why they're in that order, but that's fine. I already put them like that. So 52, I have f of x is defined to be x squared plus 2. 51, we have f of x is defined as negative 5x plus 4. The question here is to find the domain. I probably should have put that somewhere in there. Let me see if I can move this down. There we go. That worked okay. And introduce, what is it that we're doing? We're finding the domain. So for 52, again, there are no red flags. For now, there's just two of them, right? Two red flags that we're considering. Oh, there they are. Division by 0, square root. Those are the two red flags. Again, cube root is okay. Fifth root is okay. It's the even roots. Even means 2, 4, 6, and so on. So most of them we will see are square roots. In this case, there are no issues. So the domain of f, and I'll use this notation because later on we're going to have multiple functions. Domain of f, all real numbers. All real numbers. Now, on your online homework, I believe that will be an option that you can select. It'll say either domain is, and you have to put in some values to exclude, or it'll be all real numbers that you can select. But just to remind you of various notations, we can also use the following notation for all real numbers: negative infinity to infinity, interval notation. Right, so this would be interval notation, which means all real numbers, everything basically. Because for functions, we will only deal with real numbers. We're never going to plug in complex values into a function. Well, not in this class and not for quite some time, actually. So for 51, very similar, no division, no square roots. The domain is all real numbers. Or again, interval notation, negative infinity to infinity. So those are pretty straightforward, but as soon as we introduce division, or as soon as we introduce radicals, we have to be more careful. So let's go ahead and see. 58 is good. We can review a little bit of factorization in there. We here have a function by the name of g of x, defined to be x plus 4 over x cubed minus 4x. All right, so here we do have a red flag, and that red flag is we have a denominator. If your denominator is a fixed value, a constant, a number, then of course you don't have to worry about it becoming 0. But if your denominator contains a variable, then you have to worry about when, for what values of x, would that denominator equal to 0. So this is what we're concentrating on here. We're saying, when is this equal to 0? That's what we're interested in, right? Because whenever it's equal to 0, our function is going to take on this value, x plus 4 is equal to 0, or something is equal to 0. It's not going to be x plus 4 anymore. It's going to be, something, whatever that value is, some value, some number over 0. But what is some value over 0? It's undefined. And we cannot have that. Our domain tells us that we cannot have values that we're plugging in and we get undefined. That was part of the definition for domain. So we have to figure out what values give us undefined, and we'll have to exclude them. And to get those values, we have to solve this equation. Do you guys remember how to solve this?
Yes.
So what do?
We just need to take out an x. So x multiplied x squared minus 4.
Good, good. And then what?
0. So x is equal to 0, and x squared minus 4 is equal to 0. So x squared minus 4 is equal to x plus 2 multiplied x minus 2.
So, well, I think what you're saying is correct, but let me just slow down here so I can explain
Okay.
explain what I did, what we did, what you did, what you said, right? So when we're solving, we have a few strategies, but if we're solving something with a higher degree than 2, we usually try to factor it, right? That was the main approach because we know how to factor from algebra. And we have this very powerful but very simple rule that if you have a bunch of factors and the product is 0, right? Let's call them something like A, B, and C. If I have A times B times C and the product is 0, 0 is a very special number in many, many ways. Right? We saw that division by 0 undefined, but there's many, many properties of 0 that are very useful. So if I multiply a bunch of factors and the product is 0, what does that tell me?
That multiplication is 0.
But more specifically, what does that tell me about these factors that I have here?
One
of
them
those
is
numbers
0.
is 0.
Yeah, at least one of them has to be 0, right? Whatever those factors are, right? They could be, I mean, they cannot be a number because if it's a specific value, then, you know, it's a fixed value. It cannot change, but they're expressions. So whatever those factors are, one of them, at least one, has to be equal to 0. So that's what we're using here to solve these types of higher degree equations, quadratic, third degree, and so on. We try to factor everything so that our factors are linear or quadratic, because we know how to solve quadratic by few different methods: quadratic formula, further factorization, completing the square, right? We have different strategies. Square root property, like you said, in this case, we could have used the square root property. So if we can break down a third degree polynomial into factors that are of degree 2 or less, then we can solve it. So in this case, we were able to do that, or we can even break it down into linear, because x squared minus 4 also factors difference of squares, right? X minus 2x plus 2. And then we can say we have 3 factors here: x minus 2, and x plus 2. So one or more of them has to equal to 0. So the possible solutions here are x equals 0, x equals 2, or x equals negative 2. So these are the 3 values which will give me that. Right? We have to remember, why are we doing all of this? We're doing all of this to figure out what gives me 0 in the denominator. So these are the 3 values that would give me 0 in the denominator. Therefore, for my domain of G, I have to say, well, everything is fine except those. And we can use set notation to write it. Interval notation we could use, but it would be much lengthier, so we don't want to. We want to use the shorter notation. Set, so we have the set bracket. It's pretty ugly looking. Let me try and fix it. So it's the curly bracket like that. That's the set bracket. X such that, this bar is pronounced such that. And then we want to specify what it is, because everything we're dealing with for domain are real numbers. We do not have to specifically say x is a real number yet. Later on down the road, you guys will have to, if, you know, because you might have complex numbers, you might have real numbers, you'll have to specify x is real, or x is anything, or x is complex, or x is rational. But here, real numbers, so we don't have to spell that out. But x is everything except these 3 values. So x cannot equal to 0, x cannot equal to 2, x cannot equal to negative 2. So that's how we would write our domain. And I don't know if I should maybe fix that a little bit, because it doesn't fit. So let me make it a little smaller so it fits nicely, but that's what we're doing here. So x is not equal to 0. There's no particular order in which you have to list your exclusions. So I just listed them. I don't even know in what order, just like that. So that would be our set notation. But again, when you do your online homework, I think it'll kind of guide you into this notation, especially in the beginning. But it will go off of a set. All right, so let's do one example that deals with a square root, because that's another one that we have to watch out for. So let me see what we have here for square roots. 60 is all right. So for 60 we have, again, it's called capital G is the name of the function. G of x is equal to the square root of 1 minus x. So in this case, there is no division. We do not have to worry about division by 0, but there is a square root, which is an even root. So that takes us back here, right? That's the second thing we have to be careful about, the even roots. So what that tells me is the radicand, this is called the radicand, whatever is inside a radical is referred to as the radicand. Radicand has to be at least 0. So it has to be greater than or equal to 0. Square root of 0 is fine, right? Square root of 0 is 0, so there's nothing wrong with that. So that's why the equal is in there. And square root of positive values, that's fine. Square root of positive values are real numbers. The only thing where it breaks down and deviates from being a real number is when we have square roots of negatives. So this is what we have to figure out. That will give us our domain. So in our case, the radicand is 1 minus x, and we want it to be greater than or equal to 0. So again, a little bit of algebra that we have to remember. We can move the 1 to the other side or subtract 1 on both sides. So negative x is greater than or equal to negative 1. We want x by itself, so we have to divide both sides, in this case by the coefficient of negative 1. So what happens with our sign here?
It flips.
It
Then
flips.
x less than, yeah.
So it becomes less than or equal to. So a lot of fine points that you guys do have to bring back with you from algebra, right? You have to remember these things. This is the multiplication property of inequality, which tells us if you multiply or divide inequality by a negative value, you must interchange, flip the inequality symbol with its opposite. So this becomes less than or equal to 1. And this defines my domain. So I'm only interested in x's. We don't remove these. So unlike the previous question, right, we said we have to remove these. These we have to exclude. We defined our domain through exclusion. It's everything except that. Not here. Here we're not saying we have to exclude values that are less than or equal to 1. This is our domain. This is what is included in our domain. So the way that we define our domain here is, again, we will use, mostly I think you will see set notation for your homework. So here we will have domain, oh, it's not F, it's domain of G. Domain of G is all x's such that x is less than or equal to 1. So this is referred to as the set notation or set builder notation. I'll just say set notation.
Professor, would that mean the x values would only be equal to 1 and 0 and nothing else?
No. It means that x values are 1 and everything less than 1. They don't have to be integers, so they don't have to be positive, right? We're saying that if I plug in g of, let's say, negative 2, then I'm perfectly fine. Negative 2 is part of this domain. Negative 2 is less than or equal to 1. Or if I plug in g of negative 7/3, I'm perfectly fine. Or if I plug in g of negative square root of 7, I'm perfectly fine. All of these will be well defined real values. As long as your input is less than or equal to 1. We never say that it has to be an integer, nor do we ever say that the input has to be positive, right? We said that this is what defines the input, that the radicand 1 minus x has to be greater than or equal to 0, and everything else comes from there.
Got it.
Right? Because, well, I don't want to plug in the other ones, but -2, usually we would say, well, square root of -2 is not a real number, but again, here we have other things inside of the radicand. So this would be 1 minus, and then we're plugging in -2, so this would just be 1 plus 2 square root of 3. Square root of 3 is a real number, right? It's irrational, but it's a real number. So that's well within our definition of the domain. All right, so now we have these two examples, one that dealt with denominator, the other that dealt with a square root. Now let's see if you guys can combine the two together. And let me see where that one went. This is 60.
Professor, I have a question.
Yeah, go ahead.
Write it as the domain is from -infinity to 1.
That's a good question. I was actually going to do that, but then I forgot. So we have set notation, but we also have interval notation, right? They are interchangeable. You can use one or the other or both. And sometimes, usually one is easier, so we would use whatever is the quicker one to write down. But especially for your homework, since it's a computer, it's not too flexible, so you kind of have to follow the directions there. But if this were, when we go back to class and paper tests and so forth, then usually the instructors are open unless they specify which answer they want. So the interval notation for this would be the smallest number in the interval is not a number, it's a concept. They forever go to the left, so -infinity. And then we get to 1 and we include the 1. So this is the interval notation, which would be also correct answer. Good?
Yeah, thank you.
All right, so the next one you guys will try is 66, where we kind of have both of them. Is there a specific reason for that parenthesis? So for interval notation, this parenthesis and this parenthesis are different because one means inclusion, one means exclusion. So the bracket means include because we want the one included. This means exclude. Sometimes we use exclude for number. Like if this was just x is greater than or less than 1, then we would use a parenthesis, not a bracket. But when we have a concept infinity or -infinity, we cannot include that. That's not a number. So those always come with a parenthesis as opposed to a bracket. But yeah, they do mean different things. One means exclude, one means include the value next to it. So h of z is defined to be the square root of z plus 3 over z minus 2. And I'll give you guys about 7 minutes. Let's do. So make sure you consider each of the parts for this function, find their individual domains perhaps, and then consider how to put them together into a single domain using set notation, or practice and do both. But again, your book, I'm pretty sure, is going to do set notation. So go ahead and take a few minutes on this one. All right, guys. So a few of you did correspond there with some answers, and they look good. There's again few ways of writing the answers, and typing isn't always the easiest case. But again, luckily in your MML, you don't have to type everything out. They give you little keys that you can press, so you don't need to know all the shortcuts. And of course, they'll include those greater than, less than, not equal to, all that good stuff. So in this case, we will consider the two parts of this expression. First, let's consider the denominator. We know that the denominator should not equal to 0, so we want to find all the values for which z minus 2 is equal to 0, and we want to exclude them. And here there's only one such value, so this value we want to exclude from our domain. The other part is the radicand, whatever is inside your radical, right? Whatever is inside your radical is called the radicand. And if it's an even root, or a square root in this case, as is an even root, we want it to be positive. Or rather, I should say non-negative, because it could be 0. So we want z plus 3 to be greater than or equal to 0, which gives us, subtracting 3 on both sides, z is greater than or equal to -3. Now we have two parts to consider in this domain. And a lot of times it makes it a little easier if you kind of do a little number line graph to understand what you have going, especially for more challenging multi-part domains. So one of them is z is greater than or equal to -3. So if 0 is somewhere over here, -3 is here, greater than or equal to -3 means I'm interested in -3, that's part of it, or you could use a closed circle or a bracket, and I'm interested in everything greater, so that means everything to the right. Now the value that we have to exclude in our case is 2. If for whatever reason, let's just assume if it was z equals -10, or anything to the left of -3, some value over here, right? Some value that we have to exclude out here. So let me make it a little smaller so I can place it on my graph actually. Let's say I had to exclude z equals -4. Then I would not need to change anything. And I would already have my domain, because my domain is -3 and everything greater than it. So if I'm saying I have to exclude this value, well, it's not part of my domain to begin with. So I wouldn't have to do anything. I would just say my domain is -3 to infinity, or greater than or equal to -3. But that is not the case, right? My case is 2. And 2 is part of my domain. 2 is greater than or equal to -3. 2 is a value out here somewhere, right? It's part of my domain for now, but I know I have to exclude it. So I'm going to erase this, not to confuse people that look at it later. So I know I have to exclude that part, because for now it is part of my original inequality here. And to do so, I have a couple of ways of doing it. If I write using interval, we'll start with set notation. If I write using set notation, then the domain is the set of all real numbers x, such that, and then I can say x is, well, wait, it's not x, it was z. So let me use the correct letter. So set of all real numbers z, such that z is greater than or equal to -3, but we also want to make sure that z is not equal to 2. So that would be one way, and that's what some of you wrote, I believe. And the other way, using interval notation, which would also be pretty easy to write here. I'm not going to put DOH anymore. I already have that once. So using interval notation, I would have to start with the smallest value in my interval, which is -3. I would then have to go until I reach 2, which I have to exclude. So 2 is excluded, cannot have 2 in my interval, in my domain. But then I start right back up at 2, which I'm also excluding. So the only point I'm excluding is 2, but a little bit to the left and a little bit to the right, I'm okay. And I keep going to positive infinity. So if my interval contains multiple parts, we connect them with this union sign. This is or, right? So we're either here or here. That's what that means. Union. So those would be our two options here. All right, so now, let's see, it's 8:40. So this is a lengthy lesson, but the second lesson is going to be shorter. We still have one more part pertaining to this lesson. But I think I'm going to give you guys a break now, and then maybe we'll rest up a little bit and continue. So we'll do a 10-minute break, and we're going to pick back up at 8:50. So I guess 9-minute break. So get some water, use the restroom if need be, stretch out, exercise, and then we'll continue on.
Oh, fuck.
All right, guys, 8:50, so let's push on. Got a little bit more left. So let's see, there's a question. How did I get the interval notation? So interval notation in general goes from left to right, and brackets imply, so these brackets include, these brackets imply that we exclude the value that's next to them. And again, the interval notation goes left to right. So in our case, the smallest value in our interval is -3, and we want to include it because here we have that it's greater than or equal to, so equal to -3 is okay. Then we want to keep going to the right, and when we get to the value of 2, we want to exclude it. So that's why we put a 2 and we put in parentheses, but we don't exclude anything except just the point 2. So we start right back up at 2, again excluding it, and then we forever keep going to the right with infinity. And again, infinity and negative infinity we never include. We always have the exclusion bracket there. So that's a quick sort of explanation, but again, more on that. You guys will have to kind of look into the algebra review on interval notation. All right, so our next part, this is still 2-1, believe it or not. Our next part will deal with algebra on functions and also the domain for those. So when we say algebra of functions, we mean addition, subtraction, multiplication, and division. So algebra of functions, and we'll also discuss their domains. Just like you can add, subtract, multiply, and divide real numbers, you can also add, subtract, multiply, and divide functions. And we define addition of functions, for example, using the following notation. Addition of functions is defined as f plus g of x, and it is found by adding the two functions together, f of x plus g of x. Subtraction of functions is denoted as f minus g of x, and it is found by doing f of x minus g of x. Multiplication, we have a few different ways that we can denote multiplication. We can either put f times g with a small circle like that, or just fg or f cross g. Those all mean multiply. So this is f of x times g of x. The only thing is we have to be careful not to put a bigger circle, because if you remember from algebra, this means something else. F of g means composition. Composition is going to come in a little later, not today. So little dot. So these three we're going to kind of identify on their own, and then we will put the division separately. And the reason for that is the domain. So for three of these, we're going to say that the domain consists of all real numbers x that are in the domain of both f and g. So domain, all real numbers x that are in the domains of both f and g. So that's one way of phrasing it. A shorter way of phrasing it is the intersection. That's what it means. If something is in both of the sets, then it's the intersection of those two sets. Domain of f intersected with the domain of g. So that would be a shorter version of that statement. Now, division, it's still defined similarly. F over G is the quotient, and it's defined as f of x divided by g of x, but the domain is a little more, I guess, a little more parts to it. Not only do we have to consider both of the domains of f and g, but we also have to exclude whatever x's make the denominator equal to 0. We also have to exclude those from the domain, because here we create a denominator through the definition of the quotient. So I guess for me, the quicker way of writing it, I'm going to write it using notation of intersection. So we have to consider the domain of f intersected with the domain of g, and then we have to intersect it with yet another set. Let me give myself a little more space, actually. So we have to intersect it with another set of all x's for which g of x is not equal to 0. So looking at that, it's pretty difficult to kind of grasp what that means, especially if you don't remember too well what these intersection symbols are. But based on the example, you're going to see it's not half that bad. It's not, it's not overly difficult. All you're going to do is find the domain of f, find the domain of g, make sure that you take whatever is in both domains, and then on top of that, exclude any values that make g equal to 0 from that. So that would be our definition for algebra on these functions. And we're going to do just one example to kind of show you what that looks like. We're going to, let's see, which example did I like here? I like this one, so I'm going to call it number 1. We're going to say f of x is defined as 1 over x plus 2. We're going to say that g of x is defined as x over x minus 1. And we will consider part A, find the product, and for part B, find the quotient. And we'll also state their domains for both. So state domains. Now, I encourage you to start this question by finding the domain of each function right away, because you're going to need that for later. So we're just going to write those here. We're going to say domain of f. Looking at f, I see that this is a rational function. So I know there's division, and we want to exclude whatever value would make it equal to 0 in the denominator, and such value is -2, right? Because if I put -2 for my x, I get 0 in the denominator. So that should be excluded. Domain of g is similar. Domain of g is all x's such that, now here we want to exclude +1. So my set for domain of f is everything except -2. My set for domain of g is everything except +1. So if I'm looking for either addition, subtraction, or multiplication, then my set for the domain will be the sort of the end or the intersection of both of those sets. So the intersection of both of these sets, the domain of F intersect the domain of G, is going to be all x's, and now we just have to exclude both of those values, right? Because we now don't want -2 and we don't want +1. That's the intersection of these two domains. We have to consider what's in both domains. So if -2 is in one domain but not the other, we have to exclude it. Therefore, from the intersection, we have to exclude both of those values. I forgot to cross this one out. So that will be the domain for part B. This is, I mean, for part A. For part B, we will have to actually do some other thought and some other addition in there. So for part A, let's find the actual function. F times G of x is defined as f of x times g of x. So that one is pretty straightforward. It's just 1 over x plus 2 times x over x minus 1. Then you guys will have to remember how to add, subtract, multiply, or divide rational expressions, but in this case it's multiplication. However, what sometimes may happen is you get reduction in your final answer and you lose your denominator. You lose some of the factors from your denominator, but the domain still has to include those exclusions. It still has to include the original functions. So that's why I suggest finding the domain first and then working out the function. Now for part B, and this can get a little messy. Let me think how I can fit it all in here. So for part B, let's do our domain first. So I'll try to maybe color code it and fit it here on the bottom. So for part B, my domain is going to be this end sum, right? So let's consider here my domain for quotient is the intersection of domain of F and domain of G, but also intersection, we have to exclude whatever makes the denominator equal to 0. So on top of what we have now, we have to consider, well, what is my denominator? And here I'm doing F divided by G. So my denominator is function G. So when is this whole thing equal to 0? We have to exclude the values for x that make the entire g of x equal to 0. And when does that happen? Looking at g, what value of x would make the whole function go to 0?
1.
Yeah.
So if we put 1, 1 makes us divide by 0, right? If we put in 1, that makes the denominator equal to 0, and it causes division by 0, which is undefined. But what we're asking is, when is the entire function
0
equal to 0? Yeah, that's when the numerator is 0, and that occurs when x equals 0, right? So we have to exclude from our domain also x equals 0, because for that would make our function, we would be dividing by 0 in there. So let's actually write the function first, and then you might see it a little clearer. So f divided by g is defined as f function 1 over x plus 2 divided by the g function, which is x over x minus 1. So what we're saying for the domain discussion is that when this whole thing is equal to 0, we're dividing by 0. So that's what we talked about right there, that we don't want it equal to 0, which happens when x is 0. But we can simplify this a bit. We don't want to leave it in this format. We know that division by a fraction is multiplication by the reciprocal. So this is really 1 over x plus 2 times, and then we flip the other one, x minus 1 over x. Right, so instead of, so we have a couple of approaches for this, but we would want to either get rid of denominators, but that I think would be more difficult in this case. So we want to just multiply by the reciprocal instead of dividing by this fraction here. So when we do that, it gives us the following: x minus 1 over x times x plus 2. So this is our quotient function. Now, our domain, which we discussed but didn't list yet, our domain for that, our domain for, and I'll use this notation, I don't know if you'll see it, f over g. So this was the domain for f times g. This is the domain for f over g. It is again what we had before, with another exclusion of 0 on top of that. So that would be our domain here. All right. So now it's what, 9:10? Yeah, I think I'm going to finish up in the next 20-30 minutes. I think I should be able to. So we're moving on to 2.2 finally. So this was a nice lengthy lesson.
At the end, it's supposed to be x does not equal 0, right?
Correct.
Okay, just making sure.
Thank you. Let me put that in there. X should not equal to 0, definitely, because that's the one that we're excluding, as it would make the denominator 0. And you can actually see it in the final version, right? Here, we're excluding it. But again, it's best to look at the original domain, because if you look at just this final version, you see, well, 1 shouldn't be a problem, right? 1 doesn't make me divide by 0, but we still have to exclude that from the domain. All right. 2.2. 2.2 is graphs of functions. We already briefly mentioned part of this section, which is dealing with figuring out if a graph represents a function, which is the vertical line test. When I drew a circle a few pages ago, or quite a few pages ago, let's see if I can go back to that. Ooh, it was longer than I thought. Oh, there it is. This was the page that we were discussing this. So when I drew this circle and I said, this is not a function, because on the graph, we can see that there are 2 points that happen to be on the same vertical line, meaning, right, so this is the vertical line, meaning that there exists 2 different y values for the same x value, or that there is 2 different outputs or 2 different range values for a single domain value. And that breaks the definition of a function. So now we can write that for graphs in general and call it the vertical line test. We can say that if we can draw a line, so if a vertical line intersects a graph at more than 1 point, then the graph is not of a function. So essentially, I prefer to say you didn't pass the vertical line test in order to be a function, meaning that if I have, so we already saw that on the circle example, not a function. If I have a horizontal parabola, so a horizontal parabola would look something like that, right? This is a horizontal parabola. We can use the vertical line test to show that it is not a function, because we can place multiple vertical lines, but it's enough to just show it with one. We can place a vertical line that contains more than one point. So if that is the case, it means we do not have a function, not a function. Are we okay on how the vertical line test works?
Yes.
So if a parabola is goes up or down, it will still be a function, but if it goes sideways, it won't be.
Correct. So if we
There you
have a vertical parabola that goes up, down like that, then
Only
this
one
would
spot.
be a function, because anywhere I place a vertical line on this, right, it's all only going to hit at a single point. Nowhere can I place a line that crosses or intersects my graph at more than one point. So this passes the vertical line test. This would be a function, and so on. So that's just a quick shortcut if you're dealing with the graph. That way you can easier see if it's a function or not by looking at the vertical line test. Now, the last part of this lesson, we're probably just going to do one example from the book and discuss a few things from it. And I'll see if I can project it, but I'm going to remind you of a couple of things. So here we're going to say function notation, right? If we have function notation, we say f of x equals some value y. This is the input. X is the input. The result is the function value. We refer to it as the function value or the output, but it's the y value. So when we say, the words y value or function value, they are synonyms. Now, this corresponds to ordered pair notation. Ordered pair notation, again, x, comma, y, which of course correspond to points on the graph. So our goal is we should be able to kind of look at the graph and be able to read off the function notation and be able to use point notation, ordered pair notation from the graph back and forth. So I'm going to try and project page 68 here, number 12, and we're going to do a few things on it. So let me see if I have my book open. Nope, it closed down. So if you guys have your books, we are on page 68. If not, I'm going to be projecting it. All right, so we can kind of see it here. And I guess I'll use the space on the side to try and write down some of these answers. Might get a little messy, but we'll try. So for part A, and I'll go all the way here for part A, it says find f of 0 and find f of 6. And we do not have what the function is. We don't have the algebraic version of the function. We just have this guy, the graph, right? So that's all we're going from. But remember, if you have a ordered pair, then you can use that to figure out function notation. So if we're saying f of 0, then that means it corresponds to some ordered pair where the x value is 0. So what is the corresponding y value for that ordered pair?
0.
0.
Yeah, we have 0, 0. So we have that ordered pair. All we're doing is switching it to function notation. So f of 0 is 0. What about f of 6?
Also 0.
Also 0 because we have ordered pair on our graph, 6, 0 over here. So f of 6 is also 0. Part B, f of 2. What would that give me?
2, negative 2.
So f of 2, we have to find 2. There's the point, right? F of 2. So again, what that tells me is when the x value is 2, what is the corresponding y value? Well, it's negative 2. So f of 2 is equal to negative 2. And then what about f of negative 2? What would that give
1.
me? Yeah, f of negative 2. So that means the input is x, negative 2. And we have this point corresponding to 1. The ordered pair is negative 2, 1. So f of negative 2 is 1. And that's really all we're doing here. So we're going to try and do as many as we can. Part C says, is f of 3 positive or negative?
Negative.
Negative.
So let me erase these ordered pairs. F of 3, so again, we know that 3 is the x value. So we go to 3 and we see, well, where's our function at 3? And we see that our function at 3, we don't know exactly where it is, but it's somewhere down here, right? And it's not asking us the exact value, it's just saying, is it positive or negative? And we see that the function value, the y value, is negative. So we know that f of 3 is some negative value. Is f of negative 1 positive or negative?
Positive.
Positive.
So f of negative 1, we are somewhere here. That's positive. Let's try and fit part E in here, and let me erase my markings. So for part E, for what values of x is f of x equal to 0?
0.
0, 0, yeah.
The origin, right?
So f of x is the y value, right? So basically this question is saying one of them is 0, but are there any other ones?
Yeah, it's also
Yeah.
at 4 and 6.
4, 0, 6, 0.
Yeah, so we have to list all the points.
4 x equals 6.
We have to list all the points for which the y value is 0, and there's 3 of those points, right? 0, 0, 4, 0, and 6, 0. So we have 3 different x values which we have to list here. So x is 0, x is 4, and x is 6 would be the answers for part E. Now part F gets a little more interesting because here we have to have an interval. It says for what values of x is f of x less than 0. So that describes an interval, and we want to describe an interval where the y values are
0
negative.
to 4.
Yeah. So for part F, we are basically saying, where am I as a function, where am I negative? And this is where I'm negative, this piece. That's where my function values are negative. So we have to describe that interval. And that interval is between 0 and 4. Now, do we include 0 and 4?
No.
No.
We do not, because this says strictly less than.
Mhm.
So if it says strictly less than, then we do not include the actual boundary points. So 0, 4, like that. Now, what is the domain of this function?
-4 to 6.
6.
Yeah. It starts at -4. That's the smallest value where the function is defined. And it is defined at -4, so we include it. And it goes all the way to 6.
Included.
And we also include 6 because it's defined. The function is defined at 6. It's 0 at 6. There's a point there. For part H, we are looking for the range.
-2, 3.
So here, yeah, range are the y values. So we have to say, well, where is the smallest y value? That's here. Where's the biggest y value? That's here. So all these y values in between are covered. So the smallest one is -2. The largest one is +3. So the function has the range between -2 and 3. Let's see what are the interesting ones. So x-intercept, y-intercept. Yeah, I think this covers the more. Well, let's do I because x-intercepts are gonna come in pretty soon, but we already kind of did I. So x-intercept is where the graph
0.0.
crosses the x-axis, right? So we already had that question. Where does the graph cross the x-axis? Well, that happens exactly here, here, and here, right? That's the points where we cross the x-axis. So we already had those listed when x is equal to 0, when x is equal to 4, and when x is equal to 6. Those are the x-intercepts. All right, so I think that's, I'm happy with that. As long as, you know, we understand the main points about reading the graph. So I don't think I can save this page, but hopefully the other ones are going to be saved. Now I'm going to go ahead and do a roll call. So make sure that you guys are responding. Let me just set up for that. Of course, I got signed off, so I have to relog. All right, so for the roll call, I will go by your first names with the last name initial. I think that should be pretty straightforward, and I'll make fewer mistakes. So please reply here if you are here, or you can also type in the chat if you don't have your microphone working. For now, I'm accepting that. So Kenya A.
Here.
Amr A.
Here.
Amanda A. Thank you. Victor B. Victor Corral Barbosa. No Victor. Artag B. Artag Basayan. No Artag. Colin B.
Here.
Alexander B.
Here.
Gotcha. Olivia F. Gotcha. Gevorg G. Gotcha. Well, there's two Gevorg G's, so hang on. Gevorg Galajan. Okay, so both of you are here. Works for me. Thank you. Aranza G. Aranza Gonzalez. No Aranza. Joseph G. Lindsay G. Oh, Aranza is here. Okay, I got you marked. Annie G. Or Annie G. Gotcha. Chloe H.
Here.
Oscar H. Oscar Hernandez. No Oscar. Evelyn H. So if you're using the chat, I don't know who Rossi 10 is. So you gotta have a name that corresponds to a name. So yeah, I don't know who Rossi 10 is, but let's keep going. So for now, Oscar and Evelyn are not here. MDH, MD Hossein.
Yeah.
Vartkes H. Gotcha. Roman K.
Here.
Jennifer L.
Here.
Gurgen M.
Here.
Oscar M.
Here.
Adam N.
Here.
Anastasia N.
Here.
Oganes P. Gotcha. Serene P. Serene or Serene. Gotcha. Anna P.
Here.
Anna R.
Here.
Maria R. Gotcha. Alan R.
Here.
Ross R.
Here.
Andres S.
Here.
America S.
Here.
Susie S.
Here.
Susanna S. Susanna Sarkeesian. Oh, gotcha. Thank you. Michael S. Gotcha. Nagetta T.
Here.
Natalie V.
Present.
Darlene V.
Here.
Adriana Z.
Here.
Alan Z. Alan or Alan Zatikian.
I'm here.
Oh, gotcha. So let me just go over who I marked absent, because again, Rossi, you have to let me know who you were. Victor Barbosa, Artag Bazayan, Oscar Hernandez, Evelyn Herrera. And that's it. So 4 of you were marked absent. If any of you are here, let me know. All right, so we still have about 30 minutes if you guys have a couple of questions.
I have 3.
So if they're homework questions, I would prefer that we save those over Canvas, because it might be a little time consuming. But if they're like general questions, then go ahead and ask.
First question is, when is absolute value applicable? Like is it in computer science, or when would we ever actually use it in the real world?
So real world, I mean, I prefer not to go into details, because real world means like very different things for people. Like, you're not gonna walk down the street and somebody will be like, hey, what's the absolute value? And if you're doing some programming, then of course, like in business world and programming, computer programming, it'll definitely come up a whole lot. In physics, it'll come up. But when you say like real world, I'm just not too sure how to respond to that.
Second question, are most of the lectures usually going to be like 2.5 hours long, 2 hours?
So our class is 3 hours, right? We're a 6-unit class, so it's a 3-hour class time. And I probably would say that most of them will be right around there, 2.5, sometimes even 3 hours, sometimes a little less, depends on the subject matter we have to try and get through. Like today, we were probably right about 2.5 hours. So yeah, I would probably say most of them will be right around there. Yeah.
Okay. And then last, I guess it's not really a question, but I missed the last lecture and I was dropped from the class. So I was wondering if I could get added back.
Yes, I guess. Email me or write. Well, yeah, at this point you have to email me, and make sure that you tell me that you were enrolled in the class, and then it's up to you to be sure that you read the syllabus and catch up on whatever you missed the first day.
Okay, thank you.
No problem.
That's it for me.
Let's see some in the chat. So where could I find today's whiteboard material? So the whiteboard material, I will be posting that onto Canvas. So if you guys go on your Canvas and you go to Files, then you can pull up the whiteboard stuff. But not right now. I have to upload it after we're done. But you could see Tuesday's stuff. Let's see next. So Rossi or Evelyn Herrera. Let me just mark you here. Evelyn Herrera is here. Gotcha. So for Olivia, again, if it's a math question, I prefer that you write it on Canvas because it'll take me a while to go over all of your math questions, and I'd rather just do it on Canvas, at least for now. Let's see, I have a homework question. Where can I find? So if you guys have homework questions, again, write to me through Canvas and tell me which question, and that'll be probably the easiest way for me to respond to specific homework questions. I usually will not give you the overall solution or the answer. I'll usually just kind of start you up and point you in the right direction, perhaps. So yeah, on Canvas, write to me through Canvas. Okay, so you're saying it's about a lecture. Let me see. So again, if you're writing a question, I prefer you write it in a general chat so that everybody knows what I am talking to, because if you write a private chat that only I can see, and then if I start answering that, it might not make too much sense for other people. So let me see if I can bring back my screen. So 66, which one was 66? That one. Okay, so the question was, how does radical z plus 3 turn into z is greater than or equal to? So let's see if I can explain that. So here, the radical of z plus 3, right, which tells us that the radicand z plus 3 has to be greater than or equal to 0 for the root, for the radical to remain a real number. Because if we take a square root of a negative value, then we go into complex values. So we have to make sure that the inside of the radical is positive, and that's what greater than or equal to 0 implies. So that's where the z plus 3 is greater than or equal to 0 came in, if that's what you're asking. And we know that it has to be greater than because we want it to be positive. If you say less than, that means negative. So hopefully that addresses that question. Other things that you guys want to ask or discuss, again, preferably general questions that you have, not homework specific. No, everybody's quiet.
Professor, are all the homeworks that we'll be doing on the Pearson online textbook?
Please repeat that. All the homeworks, what?
Will they be on the Pearson subscription that we had to get for the class?
Yes. All the homework will be through Pearson MML. Yes.
Got it. Thank you.
No problem. All right, guys. So I guess at this point,